Hello, my name is John Carter. I gave this presentation on telescopes in the night sky to the Prescott Astronomy Club on June 3rd, 2015. I've been with amateur astronomy since 1986 when I purchased my first 10-inch Dobson telescope. I still have that telescope, but it's hibernating in my shed in the backyard right now. It's been replaced with a 12-inch telescope that I now have in an observatory in my backyard. But let's get going with the slideshow. Some of what I'm going to show you tonight has been shamelessly appropriated from Astro Course Intro by 1minuteastronomer.com. This link will take you to that internet site where you can get a little more information than what I'm going to include in this talk. Let's first talk about binoculars. If you are starting out in astronomy, then you will definitely want a pair of binoculars. There are two types of binoculars for viewing. One is for landscape viewing, like birding, and the other is for astronomy. The difference is that astronomy binoculars are designed to eliminate color fringing around stars. Aside from that, your choice of binoculars is between something inexpensive like this 8x40 Oberwerk or something a little more extravagant like the Canon 8x50 image stabilized binoculars. The next step up from binoculars is owning a telescope or viewing with a friend who has one. Things get a lot more complicated here because there are several different types to consider, and some avid astronomers have all types in their arsenal. If you want to view the planets up close, you need a planetary telescope. This kind has a long focal ratio for a very narrow field of view. Typically, this is around f10 or more and provides a field of view about the size of the moon or smaller. But this field of view really depends on the combination of f ratio and eyepiece. This kind also works well for many deep sky objects like galaxies and asteroids that are very small. And if you get the eyepiece and f ratio just right, you could get something like this. A deep sky object, or DSO for short, is anything that can't be seen with the naked eye. It can be a nebula that is 4 times the size of the moon, or a galaxy that is 1/4 the size of the moon. But for practical purposes, we'll say it is anything bigger than the moon. For this, you will need a short focal length, f5 or less, for a wide field of view of about 3 times the size of the moon or more. For example, an f10 SCT with a 40mm eyepiece will give about a 0.5 degree field of view, which is just wide enough to see all of the full moon. To see the whole of the Orion Nebula, you would need to add a 0.5x focal reducer to change the effective f ratio of the telescope to f5. Keep in mind that at some point, a small f ratio has the same field of view as a pair of binoculars. A reflector telescope is built with mirrors. Its purpose is to fold the light back on itself to make a short tube. This design allows for much larger apertures than is reasonable with refractors. A refractor telescope uses only glass lenses. The larger the aperture, the heavier the lenses become, and the more expensive they are. How you use a telescope matters. If you want instant gratification looking at stars, clusters, the moon, bright nebulas, and the sun, with the appropriate filter I might add, then viewing with an eyepiece is the way to go. If you want to see full color in star clusters, nebulas, Jupiter, and Saturn, then you need to attach a camera and get used to hours of taking long exposures followed by post-processing. However, there are some cameras that will give you full color, although somewhat lacking in detail, with exposures of less than 60 seconds and no post-processing needed. More about that later. Not all telescopes are equal. The bigger the aperture or mirror, the more light is collected, and the brighter the image. This also means that if you're doing astrophotography, then your exposure time is shorter. But let's not forget that sometimes you will want to use it. Large telescopes can be a pain in the knee, the back, the neck, and a strain on your patience. My best advice for the novice is to stay small and go for quality. We can narrow down the telescopes to 4 basic types. First is the refractor. The upside is that images are sharper. The downside is that these telescopes cost more, and it can sometimes be very uncomfortable looking in the eyepiece when the telescope is pointing up. The limiting size of a refractor is the glass at the aperture, and the price goes up as the size increases. Beyond 7 inches is for those with no children or ex-wives to support. Next is the Newtonian. This folds the light back on itself by reflecting the light from a mirror in the back to another angled mirror in the front and out the side to the eyepiece. This is a common low-cost design and can provide a very wide aperture in a reasonable sized telescope. Keep in mind that a 4-inch refractor gives about the same brilliance of stars as an 8-inch reflector. That's because the mirrors do not reflect all the available light. Next, we have a modified Newtonian, if only because of the mount. The mount or base is called a Dobson mount and can be made for less than $50 in parts. As shown here, this one is a little more expensive and comes complete with motors for both go-to and tracking. Here is the Schmidt-Cassegrain type, also called an SCT. This folds the light twice, like the Newtonian, with a twist on where the light comes out of the tube. The eyepiece is located at the rear of the optical tube assembly, or OTA. The advantage of this type of design is that a lens is put at the opening to focus the colors of the incoming light to further eliminate any color fringing in the stars and to correct for commas in the stars at the fringe of the field of view. This is becoming the most popular design with prices less than $2,000 and with the sky as the limit. The design of the refractor is quite simple. The aperture is a lens that can be composed of 1, 2, or 3 lenses combined to perform specific actions on the incoming light. A 2-lens refractor is called a doublet. A 3-lens refractor is called a triplet. The latter two are often in the class of apochromatic refractors, or APO for short. Apochromatic simply means that the 3 basic colors of light, red, green, and blue, are focused in the eyepiece to be completely free of color fringing. The right-angle adapter in the rear is only needed for visual observation to make it easier to view with the telescope in any position. For astrophotography, it is best not to use such an adapter. The Newtonian reflector turns a very long refractor telescope into a short telescope. As shown, the light is reflected off the primary mirror at the rear, focused onto the secondary mirror at the front, which then deflects the light out the side to the focuser and eyepiece. The overall length of this design is dependent on the desired F ratio. The smaller the F ratio, the shorter the tube. The F ratio is the focal length of the OTA divided by the width of the aperture. For example, an OTA with a focal length of 1,000 millimeters and an aperture of 100 millimeters has an F ratio of F10. The compound design, or SCT, has several different available features, but all are about the design of the lens at the aperture and the design of both the primary mirror and the secondary mirror. Obviously, the more complicated the design, the higher the cost, but they all manage the light in the same way. The light comes through the aperture lens, reflects off the primary mirror, is then focused onto the secondary mirror that is attached to the aperture lens, and then out to the focuser and eyepiece at the back. Now we come to the mount itself. Here we can be very critical as to what type of mount is best for a given observational criteria. The Alt-Az mount means that to track a star, you have to move the telescope in both the altitude and azimuth positions. The obvious coordinates are altitude and azimuth. At high magnification, you will be constantly repositioning the telescope. This type of mount is not suitable for long exposure astrophotography because as time goes by, the object rotates in the field of view, and this causes the object to smear. The equatorial design tilts the base of the telescope to be parallel to the north-south axis of the Earth. The reference for the position of the telescope then becomes right ascension and declination. If the telescope is properly polar aligned, it would only be necessary to move the telescope along right ascension to follow the object. Good luck with that. The Dobson mount is really no different than the AZ mount, but as you can see, it is the simplest of designs for an Alt-Az configuration. All telescopes have three basic components. There is the OTA, the mount, and what the mount itself rests on. For the Dobson mount, it rests on the Earth, so we'll bypass talking about that in this section. Let's talk about tripods and piers. The most common way to hold a mount is with a tripod. I don't care how small your telescope is, please do not put it on a cheap tripod. You need something sturdy that won't vibrate when you touch anything or when the telescope is tracking an object. Tripods make the entire setup portable enough to carry to a remote site. You can stabilize a tripod even more by hanging a heavy weight from its center. You can make a tripod more or less permanent by marking off where the legs rest on a platform. A pier is often considered to be a permanent fixture. A good permanent pier design is one that is buried deep in the ground, as this minimizes, if not eliminating, any possibility of shifting or vibrating with the building it is housed in. A pier should also not be attached to the building floor simply because any vibrations in the building, such as is caused by the wind or walking on the floor, will not be transferred to the pier. Of course, this extreme measure is only needed for long exposure astrophotography. The pier can be portable. A portable pier has three legs that fold up or detach for more portability, or you can go mobile. Eyepieces are the window into the sky. There is so much that can be talked about here that an entire 2 hours may not be enough. So here's the 1-minute talk. The more expensive the eyepiece is, the higher the probability that you will actually see all that there is to see with any given eyepiece and telescope combination. How many eyepieces you need and what kind is the real question. You can get a kit of 8 or so eyepieces to allow you to pick just the right one for the field of view and magnification that you need. I personally only use 3 eyepieces. One is a 40mm that I use to help find objects because it gives me the widest possible field of view at a low magnification. Then I switch to a 25mm eyepiece to center the object more precisely. And finally, if that's not a high enough power to fill the field of view with the object, I switch to a 15mm eyepiece. Now if that's not enough magnification, I put in a 2x Barlow to get me down to 7.5mm. The higher the magnification for a given object, the lower the effective brightness will be for that object. And using a Barlow really knocks down the effective brightness. This is probably why, if you want a really good view of the planet Saturn, you can spend around $610 on a 3.7mm TeleVue Ethos eyepiece to maximize the effective brightness. However, there is a maximum magnification for any given telescope, at which point the stars begin to look like a miniature Saturn with their own rings. Hence, you can't use a 3.7 millimeter eyepiece on just any telescope. Or you can go video. I'll talk about that later. What to avoid in a telescope? This is really easy. Don't buy a cheap department store telescope. And don't buy a cheap pair of binoculars or even one that is touted best for birding. Everyone I know who got started in astronomy as a hobby, including myself, has made the same mistake. We bought what we could afford just to get into the hobby. What is better is to use a fringe telescope until you have saved up for the best that you need for the purpose that you want it for. This might take years, but the wait will be worth it. Until then, come to our star parties and discover what each type of telescope offers, and most important, how to use it. Too many times I have been told that a $200 telescope was bought and then left in the garage simply because it was too difficult to set up and then almost impossible to see anything with. I started with a $600 homemade 10-inch Dobson that I still have after 25 years. Over the years, I have bought and sold several other telescopes. This is a 12-inch Dob on a remote pier. Here's the Galileo 2-inch refractor. This is primarily for educational purposes because it can be completely dismantled and the lenses inside can be used for different scientific purposes. Well, until now, still not completely satisfied, I own a 12-inch telescope on a pier in an observatory that I built in my backyard. And the telescope and attached cameras can be remotely operated from inside my house. You might think that would be enough to satisfy anybody. For beginners, at Christmas time, Costco and Sam's Club sell very good telescopes for less than $200 that are computer controlled for complete go-to and tracking of over 4,000 known objects in the sky. The tripod is quite sturdy and fairly easy to set up, with care. The instructions for setting up, aligning, and using the telescope are complete, but does require a lot of reading and rereading before you set up the telescope for the first time. Or find someone with prior experience to help you get started. Using a telescope can be very frustrating if you don't know where to look or what to look for. When I got started back in 1986, all I had to work with was a stack of sky charts and a book. The charts gave me positions of the stars for any given time at any given location on Earth, and the book gave me ideas on what to look for. That method is slow and very tedious. Enter the computer age. The first software that I found that let me throw away the sky charts and the book is called Stellarium. This is such an excellent application that I use it when giving talks about astronomy. Stellarium has grown up over the years and is now able to remotely control a telescope mount. And this is all for free. Stellarium has a few shortcomings for the more demanding amateur astronomer like myself. Sky Safari was created by the makers of Starry Night, which makes Sky Safari something like a little brother of Starry Night. Putting Sky Safari Pro on my iPad has become my tool of preference for controlling the mount on both the 12-inch and 8-inch telescopes. But I had to spend another $150 for the wireless device. The features of Sky Safari 4 Pro are more than adequate to give sophisticated talks on astronomy without ever looking through a telescope, and it excels in controlling my telescopes. I'm not going to be able to go into how to set up, align, and use a telescope because that could take many hours, and I don't see a telescope sitting around here. But I can talk about what you can see with a telescope. Obviously, there's the moon. Many people seeing the moon for the first time in a telescope are amazed at the detail that they see. Some astronomers do nothing but look at the moon at different phases simply because the shadows reveal more detail than can be seen during a full moon. Planets are the next thing people want to see, especially Jupiter and Saturn. The really lucky ones get to see Mars in some detail, and Venus looks just like a tiny crescent moon. All the other planets look no different than a star. Stars come in many colors. Some are clustered closely together. Some are clustered together loosely, such that it is sometimes hard to recognize that you are actually looking at a star cluster. M13 is a globular cluster that is always a treat to look at. Giant red and blue stars are easy to pick out. The golden star of Antares is a nice treat. There is the double star of Mizar and many others. In fact, almost half the stars in our galaxy are doubles. There are a few star clusters that are best viewed with binoculars, such as the double cluster in Perseus, below Cassiopeia, and the Pleiades. The Orion Nebula is probably the first nebula that every amateur astronomer wants to look at because of its size and richness of color. You're not going to see much color in visual astronomy, so that's when we turn to astrophotography or video astronomy. Seeing a galaxy in a small telescope like a 4-inch reflector can be somewhat disappointing if you expect to see spirals. The Andromeda Galaxy is too big for most telescopes. It is 3 degrees wide, 6 times larger than the Moon. So you need an F ratio of around 3 or 4, so it is best viewed with binoculars. Here's the camera shot of the terminator of the Moon, showing how shadows give a better perception of the shapes and depths of craters. Another view showing Mare Serenitatis at the bottom center, and Mare Tranquillitatis on the right. Apollo 17 landed between the two mares. Here's a full moon partially obscured by clouds. It is sometimes possible to see the moon with a telescope even when clouds nearly completely obliterate it by the naked eye. With my 12-inch telescope, I've even seen stars that appeared to be hidden behind trees. Mercury in my 12-inch telescope looks something like this, just another bright star. Unless you know where to look, you could miss it. This is probably what you are expecting to see. Venus won't look much different. When Venus is closest to Earth, you can make out the crescent shape, just like the Moon looks. This is probably what you are expecting to see. Mars is also a little bit difficult to see through an eyepiece. With a low F ratio and very large magnification, a very dark sky, and a steady telescope, it is possible to make out the ice caps. This is probably what you are expecting to see. This is an image I got of Jupiter in one of the rare moments when I got everything just right. Without the camera, the colors are not as vivid and the detail is not as clear. This Saturn image was another of my more competent times using a video camera on my 12-inch telescope. Visually, and when Saturn is closest to Earth, you can clearly make out the Cassini division in the rings. I captured Neptune and Triton easily with my Canon 60DA camera. This is a bit more dramatic and visually because you can make out the Moon, Triton, as a faint star along Neptune. This is a view of Neptune and Triton zoomed in from the previous image to show the detail. This view of a double star isn't very impressive until you zoom in on it. Viewing the globular cluster M13 through an eyepiece is way more exciting than with a camera, but so much easier sharing it with others using a camera and a large display. The Ring Nebula is popular for its distinctive shape, but the colors only pop out when using a camera. The Dumbbell Nebula looks black and white enough through an eyepiece. The colors pop out after a long exposure with the camera. The view of the Whale Galaxy and what appears to be a companion galaxy can only be seen like this with a camera. The camera used here was a Malincam Extreme 2 video camera. More about that later. I'm going to show you several shots of the Cocoon Nebula to give you a feel for the many different ways to capture it. This is a single shot with some minor post-processing, so it's really a low-resolution image. This is a high-resolution image made of many frames of long exposure stacked together and then post-processed to bring out the detail. Here, with these zoomed in and cropped views, you can easily see the difference in resolution between the two previous images. And then someone added a lot of special effects with filters and post-processing to get this image. To give you yet another perspective of the many ways to process an image, here is NGC 6559 as processed by one amateur astronomer. Notice the dust detail. And also notice that worm-looking glob just right of center. Someone else decided it should look like this. Notice that worm-looking blob now has color and a distinct shape. The dust is hardly noticed in this rendition. My favorite rendition is this one. This guy puts so much more color into everything. So as you can see, astrophotography can also be an art. Video astronomy is fast becoming the rage among amateur astronomers simply because you can get full color images in a very few seconds. Starting with something simple, to a little more complicated, to what some people are really raving about. Probably only because this is a bit more expensive, but in my mind, much better. To the very best for ultra-high definition wide-field images in less than 20 seconds. The camera alone is only $1,000, but you have to have that telescope to use it. If you own a Canon or a Nikon camera, you can attach it to your telescope and capture long exposure images for great detail and a lot of post-processing time with the right software. The total can easily run up to $3,000 for the camera, accessories, and software. For the professional and often the amateur astronomer, the S-Big cameras are the big thing in high-definition, long-exposure astrophotography. The cost can also be astronomical, reaching up to $12,000 just for the camera. You will need quite a few accessories to complete the package. Astronomers are a strange lot. We are always trying to figure out what is out there, what it is made of, and how it works.
That's all, folks.
I hope you've enjoyed this presentation and that there will be something useful in it that was new to you and maybe useful.